Good day, students. In this clip, we're going to be going over two examples reviewing rational expressions. So let's take a look at question number 1. So it says, determine the equations of any vertical asymptotes and the values of x for any holes in the graph of the function f of x equals 6 divided by x squared minus 15x plus 50. Just a real quick reminder of what the holes and the asymptotes are. Remember that the holes or removable discontinuity are the cancelled out factors set equal to 0. Okay? Any factor that you can cancel out from the numerator and the denominator, if you set those factors equal to 0 and solve, the resulting x values are your holes or removable discontinuities. Okay? And then the vertical asymptotes, this is point 1, point 2, vertical asymptotes, or you can also call them your infinite discontinuities, or your poles are the factors that remain, factors that remain in the denominator set equal to 0. Okay? So when you're canceling out factors, whatever cancels out, you set it equal to 0 and solve. That tells you your holes and your poles. Removable discontinuities. But when you're looking for vertical asymptotes, poles or infinite discontinuities, they all mean the same thing. The factors in the denominator that cannot be canceled out, if you set those to 0 and solve, that will be your vertical asymptotes or infinite discontinuity or poles. All right? So let's take a look at the problem under consideration. We have 6 divided by x squared minus 15x plus 50. Now let's factor the denominator. So factor x squared minus 15x plus 50. Okay? You can use the x game to factor this. You can also use a factoring shortcut, but I'm going to do it the long way. So let's, AC goes on top. AC is 50, and B is negative 15. The two numbers that multiply to give you the top and add to give you the bottom. Let's see. How about try negative 10 and negative 5? That works nicely. So we have x squared minus 10x minus 5x plus 50. And if we factor by grouping, take out x minus 10, minus 5, x minus 10. And the factored form is x minus 10 times x minus 5. All right, so our original function f of x in its factored form can be written as 6 divided by x minus 10 times x minus 5. Okay, now let's inspect this to see if we have any holes. Can we cancel out any factors in the numerator and denominator? Is anything common? The answer is no. So we can see that there are no holes in this problem, okay? Or no removable discontinuity. All right, so let's look at the options to see what can be eliminated. We can eliminate C and D because they indicate that there are holes in the problem. Now let's look at A and B. Which one is correct here? So remember, to find your vertical asymptotes, what you do is you set the denominator after it has been reduced to 0 and solve, okay? The factors that remain in the denominator. So all we'll do is we'll set x minus 10 to 0 and x minus 5 to 0 and solve. To solve this, we have x equals 10 and x equals 5. So this tells us that our vertical asymptotes are x equals curly bracket 5 and 10. Those are your vertical asymptotes. So let's look at the options we have here. 10 and 5. Bam, that's the correct answer. Okay, let's take a look at the second question. We're asked to sketch the graph of the function f of x equals 7 divided by x minus 1. So let's go ahead and sketch this. But before we sketch the graph, we have to just remember what the general appearance of a first degree rational looks like. So if we have f of x equals a over bx plus c, the general appearance of this rational function of the first degree, the denominator being of the first degree, is something like this. You always have an asymptote. The value of the asymptote is going to be what you get when you solve the denominator. In this case, it's going to be negative c over b. So the asymptote here is x equals negative c over b. So when you're approaching this asymptote from the left, it approaches negative infinity, the function, and then from the right, if you're approaching the asymptote, it shoots up to infinity. Okay, so this is a general appearance of a rational function, the parent rational function, with the denominator being of the first degree. Now, if there are minus here, what happens is that this portion gets reflected to the top, and this portion gets reflected to the bottom. Okay, so this is just for the first degree in the denominator with a constant in the numerator. When the degrees start increasing in the numerator and denominator, then the appearance changes considerably. Okay, all right, so let's look at this. This definitely looks like this. So the main concern here is to look for our vertical asymptotes. So if you look at this function f of x equals 7 over x minus 1, are there any holes or removable discontinuities in this function? Remember the previous problem, we said if you factor out anything and that factor can be eliminated or canceled out from the top and the denominator, then that reduced factor is your holes or removable discontinuity. If you look at this situation, is there anything that can be factored out and canceled out? The answer is no. So the only discontinuity we have is infinite or is a vertical asymptote. So let's look for our vertical asymptote. So to find our vertical asymptote, we're just going to set the denominator x minus 1 equal to 0 and solve. Okay, we have x equals 1. That's a vertical asymptote. We can also call it the infinite discontinuity or our pole. All right, so that exists at x equals 1. Let's go ahead and sketch that line. And from the left, as the function approaches this asymptote from the left, the function tends towards negative infinity. And from the right, this function tends towards infinity, something like this. Okay, so this is just a general sketch. I didn't go into what the end behaviors look like, but this is just a general sketch of what the function looks like at around the asymptotes, the vertical asymptote. All right, so there you have it. So thanks so much for taking the time to watch this presentation. Please feel free to subscribe to my channel by clicking here, and also post a comment to let me know what you think. You can give me a thumbs up, I appreciate it. And also feel free to share it with your friends via your respective social networking program. More clips can be found on mathgoodserve.com. Thanks again for watching and have a wonderful day.